Now let's look a little bit more deeper into the first law of thermodynamics. So far, we have considered various forms of energy such as heat Q, work W, and total energy E individually. And no attempt has been made to relate these different forms of energy to each other during a process. The first law of thermodynamics, also known as the conservation of energy principle, provides a sound basis for studying the relationships among these various forms of energy and energy interactions. Based on experimental observations, the first law of thermodynamics states that energy can neither be created nor destroyed during a process. It can only change forms. So, every bit of energy should be accounted for during a process. We all know that a rock at some elevation possesses some potential energy, and part of this potential energy is converted to kinetic energy as the rock falls, like what you can see in figure 239. Experimental data show that the decrease in potential energy mg delta z exactly equals the increase in kinetic energy m v2 squared minus v1 squared divided by 2. When the air resistance is negligible, thus confirming the conservation of energy principle for mechanical energy. Now consider a system undergoing a series of adiabatic processes from a specific state 1 to another specific state 2. Being adiabatic, these processes obviously cannot involve any heat transfer, but they may involve several kinds of work interactions. Careful measurements during these experiments indicate the following. For all adiabatic processes between two specified states of a closed system, the net work done is the same regardless of the nature of the closed system and the details of the process. Considering that there are an infinite number of ways to perform work interactions under adiabatic conditions, this statement appears to be very powerful with potential for far-reaching implications. This statement, which is largely based on the experiments of Joule in the first half of the 19th century, cannot be drawn from any other known physical principle and is recognized as a fundamental principle. This principle is called the first law of thermodynamics, or simply the first law. A major consequence of the first law is the existence and the definition of the property called total energy, capital E. Considering that the network is the same for all adiabatic processes of a closed system between two specified states, the value of the network must depend on the end states of the system only, and thus it must correspond to a change in a property of the system. This property is called the total energy. Note that the first law makes no reference to the value of the total energy of a closed system at a state. It simply states that the change in the total energy during an adiabatic process must be equal to the net work done. Therefore, any convenient arbitrary value can be assigned to the total energy at a specified state to serve as a reference point. Implications in the first law statement is the conservation of energy. Although the essence of the first law is the existence of the property total energy, the first law is often viewed as a statement of the conservation of energy principle. Now we will consider some processes that involve heat transfer but no work interactions. The potato baked in the oven is actually a good example for this case, which is given in figure 240. As a result of heat transfer to the potato, the energy of the potato will increase. If we disregard any mass transfer, which is the moisture loss from the potato, the increase in total energy of the potato becomes equal to the amount of heat transfer. That is, in this case, 5 kilojoules of heat is transferred to the potato. The energy increase in the potato will also be 5 kilojoules. And as another example, consider the heating of water in a pan on top of a range, which is given in figure 241. If 15 kilojoules of heat is transferred to the water from the heating element and 3 kilojoules of it is lost from the water to the surrounding air, the increase in energy of the water will be equal to the net heat transfer to water, which is 12 kilojoules. Now consider a well-insulated, that is adiabatic room heated by an electric heater as our system, which is given in figure 242. As a result of electrical work done, the energy of the system will increase. Since the system is adiabatic and cannot have any heat transfer to or from the surroundings, where Q is going to be equal to 0, the conservation of energy principle dictates that the electrical work done on the system must equal the increase in energy of the system. Next, let us replace the electric heater with a paddle wheel, which is given in figure 243. As a result of the steering process, the energy of the system that is given in figure 243 will increase. Again, since there is no heat interaction between the system and its surroundings, where Q is going to be equal to 0, the shaft work done on the system must show up as increase in the energy of the system. Many of you have probably noticed that the temperature of air rises when it's compressed, like what you see in figure 244. This is because energy is transferred to the air in the form of boundary work. In the absence of any heat transfer, where Q is going to be equal to 0, the entire boundary work will be stored in the air as part of its total energy. The conservation of energy principle again requires that the increase in the energy of the system be equal to the boundary work done on the system. We can extend the discussions that we had thus far to systems that involve various heat and work interactions simultaneously. For example, if a system gains 2 kilojoules of heat during a process while 6 kilojoules of work is done on it, the increase in the energy of the system during that process is 18 kilojoules, as you can see in figure 245. That is, the change in the energy of a system during a process is simply equal to the net energy transfer to or from the system. Now let's look at the energy balance. In light of what we discussed before, the conservation of energy principle can be expressed as follows. The net change, that is increase or decrease in the total energy of the system during a process, is equal to the difference between the total energy entering and the total energy leaving the system during that process. You can see that in an equation form, total energy entering the system minus total energy leaving the system equals change in the total energy of the system. Or as you can see, in the notation form, capital E in minus capital E out equals delta E of the system. This relation is often referred to as the energy balance and is applicable to any kind of system undergoing any kind of process. The successful use of this relation to solve engineering problems depends on the understanding the various forms of energy and recognizing the forms of energy transfer. Now let's look at energy change of the system, or delta capital E system. The determination of the energy change of a system during a process involves the evaluation of the energy of the system at the beginning and at the end of the process and taking their difference. That is, energy change would be equal to energy at final state minus energy at initial state, or in notation form, delta capital E subsystem equals E final minus E initial, that is going to be equal to E2 minus E1. Here all E values or energy values would be capital because we are dealing with the total energy of the system. Note that energy is a property and the value of a property does not change unless the state of the system changes. Therefore, the energy change of a system is zero if the state of the system does not change during the process. Also, energy can exist in numerous forms such as internal, which is a combination of sensible, latent, chemical and nuclear energy, or kinetic, potential, electrical energy and magnetic, and their sum constitutes the total energy, capital E, of a system. In the absence of electric, magnetic and surface tension effects, that is, for simple compressible systems, the change in the total energy of a system during a process is the sum of the changes in its internal, kinetic and potential energies and can be expressed as delta capital E equals delta capital U, that is the internal energy portion, plus delta KE, that is the change in kinetic energy, plus delta PE, that is the change in total potential energy. And here you can see that delta capital U, which is the change in total internal energy, equals mass times the change in the internal energies per unit mass values of state 2 minus of state 1. The change in kinetic energy or total kinetic energy, delta capital KE, equals half m, and the velocity of state 2 squared minus the velocity at state 2 squared, and the total potential energy difference, which is delta PE, would be equal to mass times gravitational acceleration times z2 minus z1, which would be the elevation difference at state 2 and state 1. And most systems encountered in practice are stationary, that is, they do not involve any changes in their velocity or elevation during a process. So as a result, you will notice that in stationary systems, the delta capital E would be equal to delta capital U, which is the change in total internal energy. Let's now look at mechanisms of energy transfer E in and E out. Energy can be transferred to or from a system in three forms: heat, work, and mass flow. Energy interactions are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a fixed mass or a closed system are heat transfer and work. Let's consider heat transfer now. Heat transfer Q. Heat transfer to a system or heat gain increases the energy of the molecules and thus the internal energy of the system, and heat transfer from a system or heat loss decreases it since the energy transferred out as heat comes from the energy of the molecules of the system. Let's now look at work transfer, W. And an energy interaction that is not caused by a temperature difference between a system and its surroundings is work. A rising piston, a rotating shaft, and an electrical wire crossing the system boundaries are all associated with work interactions. Work transfer to a system, that is, work done on a system, increases the energy of the system, and work transfer from a system, that is, work done by the system, decreases it since the energy transferred out as work comes from the energy contained within the system. Car engines and hydraulic steam or gas turbines produce work, while compressors, pumps, and mixers consume work. Now let's consider the third case of mass flow, which is denoted by simple m. Mass flow in and out of a system serves as an additional mechanism of energy transfer. When mass enters a system, the energy of the system increases because mass carries energy with it. In fact, mass is energy. Likewise, when mass leaves the system, the energy contained within the system decreases because the leaving mass takes out some energy with it. For example, when some hot water is taken out of a water heater and is replaced by the same amount of cold water, the energy content of the hot water tank or the control volume decreases as a result of these mass interactions, as you can see in figure 247. Noting that energy can be transferred in the forms of heat, work, and mass, and that net transfer of a quantity is equal to the difference between the amounts transferred in and out, the energy balance can be written more explicitly as E in, or capital E in minus capital E out, would be equal to Q in minus Q out, which would be the heat component, plus W in minus W out, which is the work component, plus the E mass in minus E mass out, which would be the energy carried by mass, would be equal to the change in energy of the system, or delta capital E of the system. Here the subscripts in and out denote quantities that enter and leave the system respectively. All these 6 quantities on the right side of the equation represents amounts, and thus they are positive quantities. The direction of energy transfer is described by the subscripts in and out. The heat transfer Q is 0 for adiabatic systems. The work transfer W is 0 for systems that involve no work interactions. The energy transport with mass E is 0 for systems that involve no mass flow across their boundaries, that is, in closed systems. Energy balance for any system undergoing any kind of process can be expressed more compactly as in equation 235, capital E in, or the total energy coming into the system, minus E out, or the net energy transfer by heat, work and mass, that is the combination of capital E in minus capital E out, would be equal to delta E of the system, which is the change in internal kinetic and potential energies, or that is delta capital E system, expressed in kilojoules. The above equation could be expressed in the rate form as capital E dot in minus capital E dot out, which would be the rate of net energy transfer by heat, work and mass, would be equal to dE of the system minus dt, which is the rate of change in internal kinetic and potential energies given in kilowatts. When you're dealing with constant rates, the total quantities during a time interval delta t, of course, are related to the quantities per unit time. As you can see, capital Q would be equal to Q dot times the delta t, the time difference, or capital W is going to be W dot, which is the rate, times the delta t, the time interval, and also delta capital E is going to be equal to dE over dt times delta t in kilojoules. As you can see, the energy balance can also be expressed per unit mass basis in simple E in minus simple E out would be equal to delta simple E of the system. In this case, the units would be kilojoules per kilogram, because we are expressing this per unit mass basis. Energy balance can be expressed in the differential form as well, as you can see in equation 239, where delta capital E in minus delta capital E out would be equal to dE of the system, or in per unit mass basis in delta simple E in minus delta simple E out would be equal to d simple E of the system. For a closed system undergoing a cycle, the initial and final states are identical, and thus you would see that the total energy of the system, delta capital E of the system, would be equal to the total energy at state 2 minus total energy at state 1 would be equal to 0. Then the energy balance for a cycle simplifies to energy in minus energy out total would be equal to 0, which also simplifies to energy in would be equal to the total energy out. Noting that a closed system does not involve any mass flow across its boundaries, the energy balance for a cycle can be expressed in terms of heat and work interactions as W net out would be equal to Q net in, or on the rate form, W dot net out would be equal to Q dot net in for a cycle. In other words, the net work output during a cycle is equal to the net heat input.